No, you guys.
Yes. Oh my God, yes. I don't think this is an example, but I do have a board picture of it being up there, but I don't think it's an
Okay, we're ready to get started? Here we go. We're ending week 6. Ending week 6. Next week we have a lecture on Tuesday and then the quiz on Thursday. Everybody on the same page? All right. I'm going to start out with this. As a matter of fact, I thought to myself, what could be, you guys ready? What could be the hardest part about Thursday's quiz? And I think this might be the hardest part. Whoops. This. Let me get this up here. Hang on. I wonder if I can make this bigger. Hang on. Let me get this out of the way. Let me go full screen. No, let's talk about this. Here are the two p-value, or the z and the t p-value Excel equations right here, with all kinds of hints. Down here is the critical value z and t equations with all kinds of hints. And I think this will be the hardest part about Thursday's quiz is which one do you use and which numbers do you use. So I just want to talk about it one more time. Norm.dist and 1 minus norm.dist depends on whether you have a negative or a positive z that you're going to enter for the first value. The test statistic z, which means your calculated z. So that determines which one to use. So right here it says, I can't even see it. If z is negative, use the top one, do not subtract from 1. If z is positive, use the bottom one, subtract from 1. Again, that's your z test statistic that you calculate, and you're trying to find p-values. But here's what I didn't highlight on Tuesday's lecture, I think Chris brought it up to me, is that I didn't emphasize that if it happens to be a two-tail, you need to multiply the result by 2. So I got that right there for either one of these. Multiply the result by 2. All right, so that takes care of doing p-value when you have a z. Let's talk about t now, you're doing p-value. Here it's all about that first number right there, which is your test statistic t, your calculated t that you calculated. After that is degrees of freedom, whether it's 1 or 2-tail. But that first number, that t test statistic, we learned that we need to drop the negative symbol in order to get the true p-value. We got to drop the negative symbol if it happens to be negative. But we also on Tuesday talked about if we want to use a negative symbol, we could then leave a negative symbol and put a dot between the t and the dist, and then you can use a negative symbol. But what we, all the way until Tuesday, was all about dropping the negative symbol for that first number and not putting a dot there between t and dist. But the whole point I'm trying to make here is, that's the equation to find p-value if it's a t. So you have those. Those are your p-value equations that you need for the quiz. I don't think of any that you'll need any others. Go ahead.
Can you only multiply for 2 for z?
Only for the z do you multiply by 2 if it's a two-tail on this p-value.
So that's for population and proportion?
Proportion. Correct. Everybody hear that? If she's saying whether you have the population standard deviation or you're doing proportions, if you're using z and you're using this equation and it's two-tail, you got to multiply by 2, your result. Go ahead.
What does it say on the top? Negative something?
Right there it says, use this one if it's a negative, what does it say? Negative z test statistic. Meaning that calculated z test statistic, if it's negative, you're using the top equation. Then below that it says, if the test statistic z is positive, you're using the bottom equation. And that test statistic z is that first number. And then the rest are 0, 1, 1. Those are easy. Now, below that are the critical value approach equations for both z and t. So the top one is equals norm at dot s dot inv, and then what number goes in the parentheses, and if you look at the notes here, same thing I've been putting on the board for the last 2 lectures. One tail, you put the confidence only in those parentheses. If it's two tail, you put the confidence plus half the significance in those parentheses.
Wait,
Say that again.
I thought it was the opposite.
Do I have this wrong? Anybody? Anybody look at their old notes? See,
No, it's
please?
right.
I think I have this right. Is it right?
Yeah.
So you've gotta use confidence plus half significance if it's two tail. Again, this is if it's C. This isn't T, this is if it's C. Meaning we have the population standard deviation or we're doing proportions. That's that equation there. Proportions is C also, so that, those top ones for p-value and that top one for critical values for proportions also. Same equation as if we have population standard deviation, the Z.
And then multiply by 2 by 2 for both, right?
Yeah, up here, this multiply by 2 is, doesn't matter if you're doing proportions or if you're doing Z for population standard deviation with a mean, you're multiplying the result by 2. If I'm incorrect there, please bring it to my attention, but I feel pretty confident that you're definitely multiplying by 2 no matter if you're doing proportions or not. Someone had a question?
Is it after you solve the equation?
Yeah, after you solve this equation, whatever the result is, you're gonna multiply by 2 if it's two tail.
What if it's the negative answer? So multiply by
Yeah, still, no matter if it's the negative at the top, or if you're gonna use a positive calculated Z at the bottom, you're multiplying the result by 2, if it's two tail. I know, this is gonna be the hardest part. But if you have this, right, I would take a picture of this, I would turn it digital, and I'd have this ready and open to go while the quiz is going on. You know it's open digital notes. And since I'm putting this up here, if this is wrong, and everybody got something wrong because I put this up here because I put something wrong in there, I'm giving you the points back, obviously, if it's my fault. So you can rely on this. What are you smiling at? Okay, she likes the fact that somebody's gonna be fair, I guess, I don't know. Is that fair? Okay. Okay, now the last equation is if it's a t-value, and you got it, and you want to use critical value or critical value approach. And to find that critical value, it's all about that first number, whether it's a one tail or two tail. If it's one tail, you have to double the significance, and this is what most people will forget. Let me repeat that. If it's a one tail, that first number is double the significance. And then the degrees of freedom is the second number. Then it says two tail, you put the significance in there for the first number only. You don't have to double it. So there's your, this is your major hint right here, because you know, like almost every equation on the second quiz is gonna ask for some kind of Excel involved. For you to use p-value approach, you're gonna have to use Excel. For you to use critical value approach, you're gonna have to use Excel. And if I ask for confidence interval approach, you still gotta use critical value Excel formulas, because the confidence interval approach has the critical value is part of the equation. So you have to use one of these formulas no matter which approach I'm asking you to do on the second test, quiz. Call it a test now. It's gonna be hard.
Is it like mainly Excel, not manual?
It's, well, for example, like, just like the homework, if we were doing a p-value question, you're manually calculating that test statistics, but then all of a sudden Excel kicks in to find the p-value to compare to the significance, so it's both. Almost every problem includes both manual and Excel. Everybody hear that? Every problem probably includes both solving manually, maybe getting that test statistic or getting the confidence interval, and then it's also gonna include an Excel equation in your answer, one of these. Probably every question. You know, I am predicting more time. I'm thinking maybe 46 minutes. What, that's not more time? You don't think? 47 then, maybe.
Wait, how many
We
questions?
may flip a coin.
How many questions is that?
You know, I haven't even started writing it, but I'm going for 15. That too many?
Yeah, that's a
How
lot.
many was the last time? It was 10, wasn't it?
I think so.
Yeah, so what's
You should
15?
do 10
12.
for consistency.
Oh, stay with 10?
We should do 12.
And 45 minutes?
Yes.
No?
I'm sorry, say again. I know that in class, I know. Can you believe it? You got another one today, it's gonna take a long time. What? What?
The final exam last semester was like 20 questions, and we had like, I don't know how many hours.
My final exam last time for 301 was 20 questions? Is that serious? That seems like, oh, because it was divided into 2 parts. I'd like to do that again this year. We should talk about that. Not today, but as we get closer, because dividing into 2 parts made everyone's grade better on an average. I was actually pleasantly surprised. So I think it's a good part to possibly split it into 2. You guys think about it? All right, so now, where are we now? Here's where we're at. Now that you have this, we're going here. Whoops, whoops, come on. I don't want you to forget, 1 week from today's the quiz. We got a lecture on Tuesday, which we're going to. You know what shocks me about Tuesday's lecture? If there's any questions about Tuesday's lecture that's going to be on the quiz, it's probably only going to be 1 question, and it's probably not going to be a hard question because I also want to include this subject on the 3rd quiz. So that's why it could be on both quizzes. It will be a harder question though when it comes to the 3rd quiz compared to the 2nd quiz. If this is even on the 2nd quiz, we'll see. Who knows? Like I said, I haven't started writing it. I'm going to start writing it tomorrow. But this is where we're now. This is going to the next level when we get to Tuesday. So the first level was doing confidence intervals. The second level was doing hypothesis testing with the 3 different approaches: P-level, critical value, and confidence interval approach. But now we're going to be heading to where we're comparing 2 different populations or 2 different samples. This is where it's getting real, and all of this is building up to that. And we have to, the same situation happens here. You have independent populations, you have populations who have both, where you know this, the population standard deviation, you have populations where you don't know the population standard deviation, and you've got to be able to tell the difference between each one of those type of equations, but it's almost the same as what you're learning all the way through. Confidence intervals, you know what you have to focus on. Hypothesis testing, you know what you have to focus on. And that's going to be the same with these next set of equations, where you were testing 2 different hypotheses instead of just 1 hypothesis. All right, so I promised to review something that I want to make sure everybody understands, and so we're going to, if you're following along, it's part 1, chapter 9, not part 2. We're going back to part 1, and I want to review this problem, but what I want to focus on is the confidence interval approach to solving this problem. Hopefully you remember this one. This is where we're making the claim, hey, we think there's an average of 3 TVs per household. So we said we're going to call how many households? 100 households in the United States? Yeah, U.S. homes. So we're calling 100 households in U.S. homes. Every phone number, there's thousands, millions of phone numbers, and everyone has a chance to be one of the 100. We randomly pick them. We give them a call. How many TVs are in your house? How many TVs are in your house? And we got our results. And we're going to take the results. We're going to compare them to the hypothesized result of 3 TVs and see if it's significantly less or significantly more. The problem says we believe there's something different than the average of 3 TVs per household. Do you hear the word different? Didn't say we think there's more than. We didn't say that think there's less than. We said different. So this is why this is a 2-tail. Mean equals 3 TVs per household. Alternative would be the mean does not equal 3 TVs. The alternative is what we're trying to prove. The null is always the opposite of what we're trying to prove, what we're assuming to be true. We're assuming that, hey, yeah, there could be 3 TVs per household. But we're trying to prove that there's not 3 TVs. There's something different, maybe less, maybe more, but it's not 3 anymore. Times have changed. That's what we're trying to say. So, to be fair, we think this is pretty important, so we're using 5% significance and a nice large sample size, which is 100 is pretty large. Don't forget, do you remember from 301, I kind of hyped on what the sample size should always be a minimum in true research. Does anybody remember what that minimum should be on sample size? Nobody? No? 30. It was 30. That's pretty much a standard rule. Don't get me wrong, you can do research with a sample size less than 30, but the golden rule used to always be try to have a sample sizes of 30 or more to have true, fair results. So now, here's our sample mean out of the 100 households we called, 2.84. We're going, oh, that's less than 3, but look, it's not that far less than 3. It's only 2.84 TVs. I mean, that's pretty darn close to 3. Now, this is where we're going to use the confidence interval approach to determine whether 3 TVs, the null hypothesis, fits within the upper and lower interval. Here's the deal. I want you to remember this. confidence interval approach can only be done when the null and alternative hypothesis is two-tailed. Remember that part. I'm not gonna trick you though, I'm not gonna give you a problem and say, okay, solve this using the confidence interval approach, and it's not even two-tailed. Because then your answer should say, this cannot be done, it's not two-tailed. I'm not gonna trick you, I wanna see work. So if I'm asking for the confidence interval approach, it is a two-tailed. You can pretty much count on that. So that's why we can do this here, because this is, go back here, this is also two-tailed. And here's the other part about confidence interval that a lot of people forget. Most of our equations, I don't have one up here, but to find our test statistic was all about using the hypothesized mean of 3, but not when it comes to the confidence interval. We're supposed to be using the sample mean, 2.84. So if you look here, it's 2.84 plus and minus our critical z, the standard deviation, which was given up to us as 0.8, divided by the square root of the sample size. Why are we using this formula for confidence interval? Because this has a population standard deviation and it's given to us. That's why we're using this formula. And we find our critical z with that formula. How did we get, let me go to this, here we go, confidence interval. There it is, slide 27 for the 3 TVs. How did we get this 1.96? Well, this goes back to week 1 and 2. We went ahead and entered the 5% into our critical value equation. Equals norm dot s dot inv. This is two-tail, so we took 95%, 5% significance, the opposite's 95% confidence, and then we added back half of the 5% significance, going to 0.975. You enter that in, 1.960. There's our critical z. We do the math on this and we go out 3, 4 digits. More digits the better, because you're about to find out how, if you don't go enough digits, you're gonna get a wrong answer, especially when they're close. In this case, look how close this was. 2.968 is the upper interval. 2.6832 is the lower interval. Notice the hypothesized 3 TVs is not part of this equation at all. That's what's different about confidence interval. It doesn't use the hypothesized number until the end. This is where you have to write a sentence showing me what it is you're comparing to either reject or not reject the null hypothesis. And what it is we compare with confidence interval is whether or not the null hypothesized number fits between this interval. Does 3 TVs fit between these two numbers? No. And because you said no, you have evidence now to reject the null hypothesis, that the average amount of TVs can't be 3. Our results from our sample show that the average amount of TVs per household is less than 3, with 5% significance. Does everybody understand how to use the confidence interval then using Z? And then we did T also, but you know what? I want to review that too. I think, is that T? No, I want to review proportions. We're going to talk about proportions again. After proportions, I want to get you psychologically prepared, because we're going to get to the hardest subject that's in this, from the first quiz to the second quiz, and that's type 2 error. A lot of people hate this, because it's not an easy calculation. I'm going to try to describe it. I'm ending today's lecture with this, because it is the toughest part of today's lecture, and we could have questions, so I want to make sure we have enough time. But before we do that, I picked a problem that I want to do as if it were a test problem. I'm on page 333 out of your book, problem number 68. It's tricky. It's tricky how to come up with the null and alternative hypothesis. In fact, I think this question is trickier than any question you might see on a test. I want you to think long and hard about this, because it doesn't give it away. You gotta try to think about, okay, what does this mean? What number is it talking about? 68 says, a politician claims that he is supported by a clear majority of voters. In a recent survey, 24 out of 40 randomly selected voters indicated that they would vote for this politician. Is the politician's claim justified at 5% level significance? Okay. First thing, there's no population standard deviation, there's no sample standard deviation, and it's giving you percentages, so you know this is proportion, and you also know you have this little extra step where you gotta find the sample proportion, because it told you how many successes there were out of a sample size of a certain amount. So you have a step involved where you gotta find the proportion of the sample. But here's the weird part. Almost every problem before this one, it was pretty clear what the hypothesized proportion would be. But it's not so clear here. Did it jump out at anybody? What the hypothesized proportion is. We're trying to prove, this politician says, the number of people voting for me is a clear majority. What the heck does majority mean? What is majority? How many, say it again.
More than 50%.
Over 50%. Over 50% is a majority. That's exactly what it means. So that is what we're trying to prove. This politician's saying, I'm claiming that the, what does it say? The voter, I'm supported by a clear majority of voters. A clear majority. This politician is trying to say, not only am I over 50%, but I'm significantly over 50%, and go ahead and measure it at what significance? What is it? 5% significance. So this person's saying, I'm over 50%. So here we go. I'm going to start with the alternative, because the politician's trying to say, I want to prove that clearly over 50% of the voters are going to vote for me. I'm going greater than 0.50, or you could write 50 with a percent symbol. It's up to you. All right, so now the null hypothesis should be obvious because it's always the opposite of the alternative. Help me out. What is it going to be? What's the null? Less than equals 0.50. All right, here's our next step. We got how many voters out of how many voters? What is it? 24 out of 40. I need calculators to help me out here. I need Excel people to help me out here. You got to tell me the numbers. 26. 26%? That can't be 26.
60%.
60. On the nose?
Yeah.
0.60? All right, you ready? I think I'll start with the manual part, which is calculating our test statistic. This is a Z calculation. I'm gonna find the test statistic. I'm going off the top of my head. Help me if I made a mistake. It's always the sample proportion, 0.60, minus the hypothesized proportion, 0.50. Is this right? 24 out of 40 is 0.60? Okay, making sure. That seems high. This equals, what is this then? 0.10, 10% over. All right, here's the denominator part. Which number am I using, the 60 or the 50? I can't hear you. 50 it is, the hypothesized. Don't get me wrong, if we were doing confidence interval, we gotta use the sample. But right now, we're just getting a test statistic, which means we're gonna use that in the critical value approach, we're gonna use it in the p-value approach. And that test statistic is gonna use the null hypothesized, the alternative hypothesized number. So 0.50 times 1 minus 0.50, that's 50% times 50%. Is that 0.25 or is that 0.025? Check it out for me, please. The sample size was 40, and then we gotta square root that whole thing. Put parentheses on this numerator, because we know we gotta do that division before we, subtraction before we divide. 0.5, what is this, 0.50 times 1 minus 0.50? What's 0.50 times 0.50? 0.25, how many zeros? Just 0.25? Oh, so this is gonna be 0.25 over 40, still square rooted. So now what's 0.25 over 40? 0.25 divided by 40.
0.00625.
So the square root of 0.00 and what was it? 625, thank you. 625. Now we're taking the square root of 0.625 and we get point, now here we go. With proportions, you're gonna need to go at least 4 digits, maybe even 5 digits. Here we go, I bet you this has a lot of zeros maybe. No, this brings less zeros, doesn't it, when we square root it? 0 point, is there 1 0? 1 0, and then what are the next 3 numbers? 7 9 0?
Well,
1?
791 if you
Well,
round it.
1.
You've been around with me on this quickly. What's your name? Divided by 0.10. Take 0.10 divided by 0.0791. It's going to be 1 point. Huh?
265.
265. Everyone agree? No. What do you mean no? Hang on. 0.10 divided by 0.0791 is 1 point.
264.
264?
2.
1.2642. We're going 4 digits. I love it. We're all on the same page, right?
Yeah.
Okay, thank you. One person. Whew. Woo! There we go. We just calculated our test statistic, our calculated Z, right?
Yeah.
Now what easy thing we can do with this now is we can find our p-value, or we can find the critical value by using the confidence or significance. Let's find our p-value. Which equation do I use? Do we want to use where are they? This one. Do I already have it? Wow, what is this? A whole nother problem somewhere. Hang on, I'm over here. Ready? Got your Excel ready. Equals norm.
No.
Oh, 1 minus?
1 minus.
Oh, thank you. 1 minus equals, because it's a positive Z, is that why I'm doing 1 minus? Look at you guys. Hey, when I get to the end of this, am I going to have to multiply by 2?
Yeah.
Oh my God. Equals 1 minus norm dot dist
No, because it's
parentheses. What's my first number?
P-value of Z, right?
Let me hear you.
1.26.
1.2642, comma 0, comma 1, comma 1. Let me repeat this, because somebody needs to enter this in Excel. Equals 1 minus norm dot dist parentheses 1.2642, comma 0, comma 1, comma 1 equals 0 point. Before you multiply by 2, what's the number?
You don't need to multiply by 2.
You don't need to.
It's a 1.
What? What?
1 tail.
This is a 1 tail, thank you, it's a 1 tail. I've still got 3 TVs in my mind, that's 2 tail. This is a 1 tail, we're now multiplying, so here's my p-value, 0 point, oh, not all together at the same time.
1031.
1031, a little over 10%, is that correct? All right, let's do the p-value approach. What's the significance?
I thought this was P-value.
Yeah, 0.05, 5%. Is this greater than 0.1031, greater than or less than 5%?
Greater than.
Greater than 0.05. Do we reject or not reject? I hear 2 answers here. Not reject.
Not
or
reject. Not re- no.
Not reject. Very good. Oh, I'm proud of you guys. There's the p-value approach. Here we go. Critical value approach. Critical value approach. We're going to use norm dot s dot inv. You just got done telling me it's 1 tail, right? I'm gonna look at my notes. Look at my notes here. What we do? We're doing critical value now. Norm s dot inv. It says if it's 1 tail, you put the confidence in the parentheses, and the confidence is 0.95. So look, here is our critical Z.
Are we doing
Our critical Z is 1.645. Is that correct? Now, my question for you is, am I first of all, am I correct on my critical Z because it's 1 tail? Am I putting just the confidence in? Do you guys look at that picture?
Yeah.
So it's definitely 1.645. Now think of a number line. Is 1.2642 closer to 0 or outside? Whether it's positive or negative, is it closer to 0 or outside the critical Z of 1.645?
Closer. Inside.
Inside, closer to 0, so it's inside. And I'm putting closer to 0, so it doesn't matter whether you're looking at 1 tail or 2 tail. Is it closer to 0 or is it outside? Closer to 0, which means we can reject or not reject.
Not reject.
Not reject. Very good. Oh, you guys are good. We got one more approach. One more approach. That we just did p-value here. We compared 10% to 5%. We said not reject. Now we found our critical value and we compared our calculated test statistics to the critical value. We said it's inside, so we can't reject.
We don't have another approach because it's 1.
Oh, we can't do confidence interval approach? Oh,
Yeah, we can.
no, it's only 1 tail. But would it work? Darn, too bad. We would have done another approach. Now, do we want to change it and make it pretend like it's 2 tail and do critical and do confidence interval approach just so you can see it done?
Yes.
Yeah? Okay, this is, go ahead, I'm sorry, go ahead. Which one?
What are we comparing it to?
The test statistic we calculated, we use this here for the p-value approach, but we also use that to compare the critical value. But how did we get this critical value? You put the confidence here, it was 5% significance, so we had to put 95% confidence here to get that number to compare that to.
But how do we
Okay, think of a number line, zeros in the middle, 1.264 is right after 0, and then 1.645 is after that. Since this is inside of that closer to 0, we can't reject this. Boom, 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 boom. All right, do we really want to pretend this is a two-tail and confidence interval? What we'll do is we'll do confidence interval, and you see it won't work because it is a one-tail, is what you'll see, but we can just try it. You ready? But again, if this is for a quiz, it would be on a two-tail, not a one-tail, but we can see how it works. Okay, we gotta go with the sample mean. Remember that, you've gotta use this number, the sample proportion. So the sample proportion is 0.60 plus or minus, you've gotta use the critical Z that we calculated up here, 1.645 times, now, here we go. This is just like confidence interval for proportion. You remember these? Nick, go ahead.
That would be different because it's two-tailed now, right?
Oh, no, I'm pretend. Okay, hang on. I want to not, what I want to do is I want to pretend like it's two-tailed that we're doing this, but I'm going to treat it like it's one-tailed to show you it doesn't work. We're going to come up with an interval and we'll see if 0.50 fits, but because we're treating it like one-tail, it probably will end up not fitting and say reject when really we're not rejecting. But really these are so far away this may work anyway. Don't tell me I got to do that. But good point. If we were switching this to two-tail, that would switch this because we would end up going to that, which would then make it 1.960. Right now, we're gonna go ahead and keep it a one-tail, but we're doing a confidence interval even though this is not how we would do it on a test. So the confidence interval is the sample proportion plus or minus the critical Z times the proportion standard error, which would be, see, this is it. We got to use the sample proportion here. This is where people will make mistakes and use the hypothesized proportion, not 0.50, 0.60 times 1 minus 0.60 divided by, how many were in the sample, 40? 40 square root the whole thing. Get my calculator out. Here we go. 0.60 times 0.60 should be 0.36. 0.6 times 0.6 should be 0.36. There's 0.36 divided by 40. It's going to be 0.9 or something like that, divided by 40. Oh no, what am I thinking? It's going to be 0.009. Square root it. Now square rooting it. 0.0948. 0.0948. What's the next digit? 868, so 7. There we go. Times.
Why did you do 0.6 times 0.6?
You ready? The sample proportion is 24 out of 40, which is 0.60. For a confidence interval, you've got to use the sample proportion here and here. You can't use the hypothesized proportion. Most people will accidentally use 0.50 here, the hypothesized proportion, but for confidence interval, 0.50 doesn't come in. The hypothesized proportion doesn't come in until you're comparing if it fits or not.
No, but why did you do 0.6 times 0.6?
Well, 0.6 times 1 minus 0.6. Oh, thank you. Thank you. I made a mistake. I didn't understand what she was saying. 0.6, not times 0.6, times the opposite of 0.6, which is 0.4. So now 0.24. 0.24 divided by 40. 0.24 divided by 40. 0.006, now square root it. 0.07746. 0.07746, is that right? 0.07746. Now that gets multiplied times your critical value, gets added and subtracted from 0.6. So 0.00746 times the critical value, which is 1.645. This is what gets added and subtracted. So now this turns into 0.1, help me out, 274. I'm going to add and subtract 0.1274 to 0.6. This is going to be, ready? 0.7274, and the lower one's going to be, here we go, make this a minus, added to 0.6, and the lower one's going to be 0.4726. 0.4726. Now look what's happening. We're going to get the same answer. Does our hypothesized proportion of 50% fit in the interval between 0.7274 and 0.4726? Yes or no? It does fit, and whenever it does fit, you cannot reject the null hypothesis. This one said not reject, this one said not reject, and this one said not reject, even though we would not be using this one if it's not two-tailed. But just to show you, if these were closer together, this 60 and this 50, this possibly would have ended up with the wrong answer. It probably would have said reject when really it should be not reject. That's what happens with one-tailed swords. All right, now that we did all that review and you're prepared for the next test pretty much, we have to do type 1 and type 2 errors. First I want to define them so you know what we're talking about. I'm going again back to part 1 PowerPoint, going all the way to slide 9. I think it's 9. There it is. Type 1 error. This one's easy. This is where you reject a null hypothesis, but you were wrong. And this is called a type 1 of error. And the probability of doing that is very easy. It's whatever the significance is in the problem. The opposite of the confidence. If all you give is the confidence. So if I said to you, hey, this problem we're going to do with 96% confidence, what's the probability of you making a type 1 error? Exactly, I heard it. 4%. Whatever the significance is in the problem is the probability of you making a type 1 error. That one's easy. Whatever the significance is. All right? Type 2 error. Now don't forget, type 1 is where you rejected the null hypothesis, but you shouldn't have. Type 2 is where you should have rejected the null hypothesis, but you didn't. Everybody hear that? Failed to reject a false null hypothesis. I'm going to put it in my words. You should have rejected the null hypothesis, but you didn't reject the null hypothesis. You went ahead and not rejected a hypothesis that was incorrect. That's called a type 2 error. This is much harder to calculate. Okay, so you ready? The type 2 error is when you should have rejected a null, but you didn't. Type 2 is where some calculation happened and it caused you to not reject the null hypothesis, but really that null hypothesis should have been rejected, that something went wrong, whatever it may be, and that's called a type 2 error. By the way, the most common way type 2 errors are made is from too small of a sample size. But that's not even in this. I'm just telling you from reality.
See that example you gave us with the 50% whatever, like claims?
Yeah.
Is that gonna be on the test quiz?
Well, something just like it, yeah, but not so hard for you to be able to figure out what the null hypothesis is and the alternative. Is that what you're worried about?
Yeah.
Yeah, that won't be as hard as that. You had to pull the 50%. You had to know what majority meant. That one was hard. That's why I thought that one was hard. Did you think that was hard? Did you think that was hard?
Well, when you said 50%, it seemed easier than it
Yeah.
was before.
Yeah, I think that's why even the problem on the test, it will literally say, this politician thinks he will get significantly more than 50% of the votes. So instead of saying majority, it will say 50%. Okay.
So we have to take that as the alternative.
That would be the number 50% would be used in both the alternative and the
But it would
null.
be more than 50% would be the alternative.
Would be the alternative, because that's what the claim is.
What did it use? Like what number you used?
In real life?
No.
Oh, what do you mean what's it used for?
Type 1, type 2 error.
Oh, because you gotta, here's what the question's gonna be about type 2 error. It says, hey, you went ahead and did some research, and you went ahead and did not reject the null hypothesis, afterwards, we found out that the null hypothesis should have been rejected, what's the probability you made that type of an error, called type 2 error? You gotta be able to calculate that probability. If the question said, hey, you just got done doing this research and you rejected a null hypothesis that should not have been rejected. It was a true hypothesis. What's the probability of that happening? That's a type 1 error, and all you gotta do is say the significance, whatever the significance is, that's your probability. But type 2 error, hey, you did some research, you didn't reject a null hypothesis, and you should have, that's a type 2 error. What's the probability of that happening? Are you ready? Because this is the part that's hard to calculate. I'm going to the second PowerPoint, part 2. I'm going to slide 21. Is this the one? Yeah, 21. I'm going to refresh the story here. All right. Do I need to refresh the story? Where is it coming from? I don't know. Hypothetically. You ready? Let's say our hypothesis was all about 52. And here's the bell curve of 52, but that was just our hypothesis. When really the mean of the population ended up being 50, significantly below 52, but we didn't reject 52. We ended up, here's the significance in this bell curve, we ended up closer to 52 than we were outside the critical value. So let's say we were right there and we didn't reject it. This is a type 2 error. We should have rejected it, but we didn't. But the only way to calculate it is afterwards, when you finally find out what the true mean was of the population, then that can be used to calculate what the probability was of making that error. The calculation's all about finding that area from that dotted line where the significant was on the original equation to the right of that bell curve area on the new bell curve, now that you know what the mean is. That's the hard part. This little part right here, if you could just take 50% minus that, you would have all of this. You could just maybe figure out that part. But you have this area right there that's got to be included. So you have to use this. You got to find what this number is right there, where that dotted line is to the right, to figure out that area for a type 2. So here it is. Remember, your numbers are 50 and 52. What are the other numbers? Hang on, what involved here? Blah, blah, blah. Oh, the 6 and the 64. I can't remember the story, but here it is. The sample size is 64. The population standard deviation is 6. You ready? Everybody with me? This problem, hey, we've sampled 64. We know the population standard deviation is 6. We're using 5% significance, and we were using a hypothesis of 52, greater than equal to 52, and the other one was less than 52. But 52 was our number. But now that it's over with, when we're trying to figure out what the probability of a type 2 error is, and we know now the mean is really 50, we can calculate this. Ready? First, we find what this number is from the 52 bell curve. That number right there. So 52 minus the critical Z, which is 5%. We put 5% in here. It's a one tail, so 0.95, 1.645. There's the formula to get our critical. Times the standard deviation, which is 6, over the square root of 64, which would be 8, right? 6 divided by 8 times that. We do all the math on this. That number on the number line, using the 52 bell curve right there, is 50.766, that number right there. Now you got to turn around, flip it. Use that number you just found, 50.766, and figure out what that would be to the right on the other bell curve. You got to go to the other bell curve now, the 50, and take 50 minus 50.766, or vice versa. 50.766 minus 50. We just switched bell curves. This is hard. I can tell by a lot of looks here. I'm losing a few of you, but I'm going to go through it again. I'm going to finish it off, and we'll go through it again. We're on the 50 bell curve now. We took the number we just calculated, 50.766, minus our new number that we now found out about the population, that mean was 50, not 52, divided by the same standard deviation, the same square root of the sample size, and we get and we get 1.02. We calculated 1.02. Now ignore what's on the right there. That's if you went and looked at the Z-chart. We're not going to use the Z-chart. We're using this. It's a positive 1.02. So equals 1 minus, because it's a positive 1.02, norm dot dist 1.02 comma 0 comma 1 comma 1. There's my p-value. That p-value is that percentage underneath the bell curve, if the new bell curve from that point to the right. It includes even that little part right there. That is the probability of accidentally having a type 2 error. Wow. Everybody want to see that again? Are you ready? I'll enhance the story a little, I'll enhance it, because I want to make sure you can calculate this. Let's figure out where this, where did the 52, what's the null hypothesis come from here? Suppose we correctly rejected that we thought we correctly, or we correctly rejected a null hypothesis that's greater than or equal to 52. It's one tail. But in fact, the true mean was 50. It wasn't 52, it was true 50. What's the probability of you conducting a type 2 error, which means you accidentally didn't reject the 52 when you should have? Everybody with me? That's the question. Also, what else is given to you? The standard deviation is, standard deviation is 6, the sample size is 64, and we're using 5% significance. So now, let's go back. It says we rejected 52, the null hypothesis about greater than or equal to 52, but a type 2 error would be if we didn't reject it and we should have. Because we found out the true mean is 50. We're gonna base our first calculation on that hypothesized mean, 52. And we're gonna find the margin of error and subtract it from 52, or is it added? Added to 52, right? Is it added or subtracted, guys? Let's go back and look. Subtracted, because 50 is less than 52. So here we go. 52 minus the critical Z, which we calculated by using, critical Z, norm dot S dot INV. It's a one tail, so we put the confidence in, 5% significance, 95% confidence, gives us the critical Z of 1.645. We take that 1.645 right there, and we multiply it times the standard deviation given to us, 6, over the square root of the sample size given to us, 64. So we went ahead and found the lower interval of that 52 based on 5%. And right there is that lower number, 50.766. Now, you take that number and compare it to the 50, the new mean, and figure out what the p-value is. So that's what this is doing. 50.766 minus the new mean, 50, over the same standard deviation, 6, divided by the square root of 64. This gives you 1.02. Now you plug it into your p-value formula. Equals, it's a positive 1.02, so we got 1 minus in front. Norm dot dist, the 1.02 we just calculated, comma 0, comma 1, comma 1. It's a one tail, so we don't multiply this times 2. That is the p-value from that spot, 50.766 to the right. That right there to the right is just being calculated by entering it in that formula, 0.1539. The probability of you making a type 2 error on this problem, once we found out that the true mean is 50 and not 52, about a little over 15% chance of making that type of error, which is pretty high. A good way to lower that is to increase your sample size. All right, that was the hardest part that could be on the quiz. Do you want me, I want to repeat what slides were key on this. It was part 2, chapter 9, and the key part of it was, I'm going, slide 21 and slide 24. Let me repeat that. Slide 21, slide 24, and slide 25. Those 3 slides are the 3 main slides of being able to calculate a type 2 error. Hey, what though, let's say you didn't reject a null hypothesis and you should have rejected it? Or, oh wait, I'm sorry, I wanna make sure I say that right. You rejected a null, you didn't reject a null hypothesis and you should have? That's a type 1 error, so what's the probability of that happening with this problem right here? Probability of making that type 1 error, what is it?
Was it that type
5%, very good, you guys.
Hey, what did
You were listening, sorry, go ahead. Who said that?
Wasn't that type 2? You said if you should have rejected it, but you didn't?
A type 2 error, but we did reject it, but if we didn't reject it, we should have, that's a type 2 error, and this is the probability. Now listen, we didn't multiply this times 2, is because it's a 1 tail. The original, if you go back 3 slides, it's a 1 tail, and that's why we didn't multiply that times 2. If it were a 2 tail, it would have been more like 31% or 30.7%.
Didn't you just use the wrong definition just now? You said, yeah, accepting a null when it was false.
I didn't know, I said accepting a null. I can't believe those words came out of my mouth. I
Well,
have to go back and look. Did I really say
Not
accept?
that word, but I think you said that.
You did.
Oh, stop. You're the person who says we never did confidence intervals for Z.
Oh, yeah, I took that back.
I'm sorry, Jancy, say that again.
Oh, so which one's a type 2? You just define.
You ready?
Yeah.
Okay, you're right, I could say this wrong. It's either, oh, you know what? Here's a slide, right here. This one, which one's type 1, which one's type 2? Go to slide 11 from part 1. It will literally tell you which one's part 2, a type 1 error, and which one's type 2. Here's type 1. You rejected the null, and the null was true. You should not have rejected it. That's type 1 error. Type 2 did not reject the null, and the null was false. That's a type 2 error. So again, that's part 1, slide number, it looks like 17. Is that what it says on the end? 11? 11. Slide 11. Thank you. So another question. Yes.
For the equation that you got for 1.02, what's that called?
That, you know, that equation, it happens to be the confidence interval equation, but the only thing about it is, we used the null hypothesized number in that equation. That's the only thing weird about it, but it's the exact equation for the lower interval, the confidence interval equation. It's really what it is, except we're not using the sample mean, we're using the hypothesized mean. That's the difference.
Okay, so like, when we find, what would that be? I'm just writing a formula, so I'm gonna say called, so I can plug it into the second one.
Hang on, what do you mean? What? I have to give it a name?
Yes.
I don't know what to call it. How about the type 2 error formula?
Wait, what's
Alright.
the type 1 error formula?
There is no type 1 error formula, because type 1 error is just whatever the significance is. That's the probability. The type 2 error formula is this one combined with this one, right here, these two. It's the confidence interval formula, that's all it is. It's just a matter of knowing which numbers to use though.
On the last slide, what was that B?
Hold on, just spend a number.
Hang on, everybody, I can't hear him. Go ahead.
You see the B symbol in the middle of the green? What is that? It says so B.
I'm colorblind, but I think this is green. Is this what you're talking about?
Up and down a little?
That's green? That's green.
That's like a bit green, yeah.
That's
Okay.
like a.
All this is doing is saying, once you find that number, now you gotta compare it to that number.
What does the B mean? It says so B.
Oh, that stands for the probability of a type 2 error. To calculate that probability, you gotta compare what you just calculated to the mean of 50. That little symbol called beta, I think it's called beta. I think it's called beta. That symbol is whatever the probability of a type 2 error is. That's what that symbol represents.
So we're doing critical Z?
Yeah, you got whatever the significance is, you gotta use the critical Z in that formula. Add that to your equation. That number right there is critical Z based on the significance or confidence. But that's the same thing in confidence interval, you gotta use critical Z.
Something about multiplying it.
But we are doing a p-value here. When we got to this number, the probability of what would be for a type 2 error, if it were 2 tail, we would have multiplied times 2. but it was 1/2. I don't know what you mean by that. Yeah, we use this equation to get that, and this equation to get that. So both of these Excel equations are involved in calculating type 2 error.
So that's the end. Multiply by two would be the last.
That's right, that 0.1539 is the end. That's right. All right, you ready for the end class? Except for a couple more questions, Victor. Which one?